So the next trend I want to look at is ionization energy and different aspects of ionization energy. So first of all, what is ionization energy? Well, it's the energy needed to remove an electron. So it's the minimum energy needed to remove an electron from an atom or ion, technically in the gas state. So, we're going to be removing electrons. Now, we should think more specifically, right? We're going to be removing a valence electron. This is an endothermic process, right? So it requires energy, right? Not surprising, right? So we have to absorb energy for this to happen. We're going to be removing valence electrons, right? These are your outer electrons. These are going to be the easiest to remove, have the lowest ionization energy. And if we can lose more than one, so if we have a species that can take on, say, a positive 2 charge, we treat each ionization energy separately. So, for example, if I lose 1 electron, so I have my metal plus 1 ionization energy, we get a metal plus 1, and we release electron. So this has an ionization energy here. If this positive 1 ion has a second ionization energy, or so it's given more energy, it can lose a second electron. That's a second ionization energy. So we have first ionization, second ionization, etc. So this is from a neutral atom. A second would be from the positive 1 ion. We could have a third to remove it from the positive 2, so if we took on a positive 3, etc. Every time we do this, this is going to be the easiest, the lowest energy. This is going to be harder. So every electron we remove is going to take more energy. So let's look at the trends in first ionization energies. So if we sort of zoom in on this table here, so again, we're going to look at across the main groups and down the main groups. So let's look at period 2, starting at lithium. What we see is generally, now these are trends, so you're going to see little blips here where it doesn't follow the trend, but generally speaking, as you go across, the ionization energy gets higher. So in other words, as it goes across, it gets harder to remove the electrons. Now, why is that? Well, basically, it's size. And we'll talk on the next slide, we'll talk a little bit more about this. But remember, the atoms are getting smaller, the electrons are held more tighter, it's going to be harder to remove it. If you look at the trends going down, you see the ionization energies get smaller as you go down. Again, think of it in terms of size. The atoms are bigger. The electrons are further away. They're not as held to the nucleus as strongly, so it's going to be easier to remove them. So if we can think about the size trends, it gives us a good insight into the ionization energy trends. Okay, so let's look at these a little bit more detail. So, the larger the Z effective, the more the energy it takes to remove it, right? So, when we talked about the size trend, we said that as you go across, Z effective gets bigger, right? That causes the size to get smaller. It's going to cause the ionization energy to get higher. So Z effective goes up, size goes down, ionization energy goes up. This is as you go across. As you go down, again, the electrons are further from the nucleus. They're going to be easier to remove, so you see it go down. Again, going across, the Z effective goes up, becomes harder to remove it. So to summarize, You go across, ionization energy gets higher, which means it's harder to remove it. Atoms get smaller. You go down, atoms get bigger, ionization energy gets smaller, which means it's easier to remove that electron. Okay, so now let's turn attention to sort of a related ionization energy trend, and that is what happens if you look at what we call successive ionization energy. So if an atom can lose more than one electron, what's the pattern we see between the first ionization or losing the first, the second ionization energy, etc.? Well, I already gave you the first basic idea, and that is each successive electron costs more energy. So if we look at, sodium, for example, right? Sodium only loses one electron, right? It forms a positive one ion. It's pretty easy to remove the first one. Notice how much energy it would take to remove a second one. Now, this is not a great example to show this, because what that tells me is that it's never going to remove that second electron, because, again, it's not a valence electron. Now, what about magnesium, which has 2 valence electrons? It can lose 2 electrons fairly easily, but notice it does take more energy to move the second one. So we get a first one of 738, a second one of 1450. But once you get rid of the valence electrons, now you see this huge increase, just like you saw here, in order to remove that third, or to remove something that is not a valence electron, to start removing a core electron. Now, what's going on here? Well, first of all, after you remove the first electron, now we have the same number of protons, but we have fewer electrons to attract. So each of those fewer electrons can be sort of pulled in a little bit tighter. So as you remove electrons, the remaining electrons get pulled in a little closer, which causes the atoms to get a little bit smaller, which means the electrons are held a little bit tighter. So that second electron takes a little bit more energy to remove. So it's always harder to remove that second and third electron. So as long as we're removing valence electrons, there's sort of a normal increase. Now, it might not always be the same, so you might think of it doubling, maybe a little bit more than doubling. It just depends. But it's sort of what we might consider, if we look at the data, sort of normal increases. But what we should notice is once we finish removing the valence electrons, we see a huge increase in the energy to remove a core electron. And what this tells me is, if I look at a pattern, is it tells me, okay, I've removed all the valence electrons and now I'm trying to remove a core electron. So let's look at sort of all the data here. So this is looking at the second period elements, right? So sodium, the third period element, sodium through argon. And so we know sodium, right, has 1 valence electron, group 1. Magnesium, 2 valence electrons. So we see that if we look at where we see the big increase, so we see this huge almost tenfold increase here. Right? So this tells me that, okay, I'm no longer trying to remove a valence electron. Magnesium, we see like a normal increase, like a doubling. And then all of a sudden we see this huge increase. Well, that tells me that I've removed all the valence electrons. If I look at aluminum, if I'm just looking at this, okay, I see, it's sort of a reasonable increase. Maybe there's a big jump between 1 and 2. Then we get a nice little, almost doubling. But then we get this sort of really big increase. That tells me I've run out of valence electrons. Now I go to 4 valence electrons again. We see sort of an increase, a normal increase, a normal increase, a normal increase, then a huge increase. And so even without putting a label on this, if I just gave you an isolated set of data, like say this, and I wanted you to tell me how many valence electrons does this species have based on these ionization energies, you should be able to look at this and say, okay, well, this is kind of a normal looking increase, kind of a normal looking increase, yeah, normal looking increase, normal. Okay, here we get a big increase, much bigger than what we've seen before. So at this point, I've run out of valence electrons. So this species has 1, 2, 3, 4, 5 valence electrons. So whatever this atom is, it's in group 5. Now, I might not know which group 5 element it is unless I know which period it's in. But by looking at this kind of data, I could say that based on these ionization energies, how many valence electrons a species has. So these are some of the things that we see with successive ionization energies. Now, to wrap this chapter up, and this set of chapters up, I just want to summarize again these trends that we've looked at. So first of all, atomic radii, moving down a column, we get bigger size. Across the row or the period, we get smaller size, right? Because of that increasing effective charge. Now, look at the relationship between size and ionization energy. As we move down, size goes up, ionization energy gets smaller, right? So we see this relationship. If we go across the column, size gets smaller, ionization energy gets bigger, becomes harder to remove it, right? So we see these trends moving in opposite directions. The size gets bigger, ionization energy gets smaller, size gets smaller, ionization energy gets bigger. So these two trends are really closely related. Now, there are a couple of other trends that we didn't really talk about, and I'm not going to talk about them too much. One is electron affinity, and the problem is the trends are not great here. There's another property that we'll look at a little bit later in an upcoming chapter called electronegativity that kind of looks at the same idea, and that's the energy that's involved in gaining electrons, and it has a little better trend to look at. So really, we're not really paying too much attention to electron affinity. Now, metallic character, this we've already sort of learned about in the sense of where the metals are, right? So if you look at the periodic table, we know the metals are located, right, in the middle to left side of the periodic table. So the most metallic elements, right, as you go down a column, things get, quote, more metallic. As you go across, they get less metallic, right? So things get less metallic as you move across. And this is related to ionization energies, right? So as things become more metallic, the ionization energies get smaller. It becomes easier to lose electrons is one of the things that you see when things become more metallic. So as ionization increases, as you go right across, right, as they do, we see they become less metallic. Right? Now, I'm going to go back and just look at a periodic table real quick and just point out this idea of metallic character. Just point out some big ideas here. Okay, so let's look at the periodic table real quick. So we've seen these trends, and we can look more globally at this. So let's think about size. So yes, we know that size gets smaller this way and gets larger this way. So if we look at this as a whole, right, your biggest atoms are going to be down here, your smallest atoms are going to be up here. So this means your biggest atoms are going to have your lowest ionization energy. Your smallest atoms are going to have your highest ionization energy. And not surprisingly, right, your most metallic elements, so your metallic nature, is going to increase as you go this way. So these down here are going to be your largest, lowest ionization elements. These are going to be your most metallic elements up here, right? These are going to go here. They become less and less metallic, and these are all non-metals, right? You know, notice generally as you go down, Notice some of these main group elements. You go from non-metals to metalloids, and you get eventually down here to things that we think of as metals, like lead, tin, right? So you can see the metallic nature increasing as you go down, right? You get to things that have lower ionization energy. And so a lot of these trends really sort of link together, and we can really think about that. All right, so I'm going to bring this session to a close. And as you have questions, as you're going through both these chapters, and again, I've sort of moved in between 8 and 9 in some of these chapters, but a lot of the topics are really interrelated with each other. So as you have questions, reach out. I'm here to help.